When we introduced IP, we mentioned that the value of an IP address increases in the same pattern as the ticking of a clock. One of the special IP addresses we'll be discussing today is in fact one that signifies the beginning of time. 0.0.0.0. Hello guys, we'll talk about special IP addresses. From now onwards, we shall be using new terms to refer to devices on computer networks, host and node. A node on a computer network is any device connected to that network. This includes hubs, routers, switches, desktop computer, servers. Basically, any device on a computer network is a node. A host is a node that participates in user applications, either as a server, client computer, or both. Devices like a desktop computer, router, layer 3 switch, and server are all hosts. Basically, a host is any device on an IP network with at least one IP address. This means hubs and layer 2 switches cannot be called hosts. On this network, we have 13 nodes and only 7 hosts. Lastly, the term end system or end station refers to any device located at the edge of a network, such as these. When we say end-to-end communication, we mean communication between one end device and another. Moving on, please take a moment to hit the subscribe button and turn on bell notifications so you'll be the first to know when we release a new video like this one. You know that moment you're about to fill a form and you have a spot for a spouse? Well, if you're single, you're most likely feeling not available. However, to do this using an IP address is simple. Just fill in 0.0.0.0. Generally, the IP address 0.0.0.0 means an unknown, invalid, or non-applicable target. On computer networks, the meaning of this address may vary depending on whether the host is a client computer or a server. What does loopback mean? To loopback means to send something from yourself to yourself. It's like throwing a boomerang. In computer networking, any packet sent to a loopback address never leaves the device that originated it. The entire process of signal generation, transmission, reception, and processing takes place within the device itself. What are these loopback addresses? This is a server with an IP address. Let's visualize this server as a building such as a shopping complex. In here, there are shops. In these shops, there are attendants. James knows and carries out the procedures to help customers buy electronics from shop number 1. Danielle carries out the procedures for the use of catering services in shop number 5. Mohammed knows the procedures for buying clothes from shop number 12, and so on. In networking, this building is a server with IP address 192.168.1.1. The shops define the services provided by the server. The attendants are the protocols or applications that need to run for those services to be delivered to clients. And finally, the shop number defines the port number of the service you need to use. Every application running on a server can listen to only one IP address. This IP address does not have to be unique, but the port number must be. So, if a client needs to use web services on this server, it should connect to 192.168.1.1 on port 80 or 443. Every application on the server can be used externally by other devices on the network. But if you need a service to be accessed only by the server itself, use a loopback address. A loopback address for IPv4 is any address that begins with 127. If a user application is configured to listen to 127.0.0.1, it makes this application accessible by processes running on this server alone. This loopback address is called local host address. Since loopback addresses allow a device to send IP packets to itself, they are used for diagnostics, such as testing if a device is correctly configured to implement TCP/IP, or if the network card of a device is faulty. Web developers use loopback addresses to test their applications locally before deploying on an actual web server. If any host attempts to send a packet to 127.0.0.1, this packet will never leave the local host because the destination IP address is a loopback address. Finally, since every application can only listen to one IP address, what happens if this application is configured to listen to 0.0.0.0? In this scenario, the application will listen to any IP address configured on this local machine, which includes all IP addresses on physical interfaces and loopback addresses. We'll learn about the few remaining special IP addresses in the next video. Until then, thank you for watching. Hello guys, today we'll talk about collision and broadcast domains. Let's play a game called Electrocution. In this scenario, all cats are connected directly to the cable that supplies power. When we turn on the power source, all the cats will feel the shock since all of the wires are joined together. In networking, these cats are said to be on the same collision domain since they receive the shock together. A hub provides this functionality for computers, as every device on the same collision domain receives the same message sent from a source. In the second scenario, we install a switching unit here so that all cats will be isolated from one another. When we activate the power source, no cat will be electrocuted at first. We can electrocute any cat of our choice by performing the right connection. On computer networks, we say they are on different collision domains based on that isolation, and a switch provides this functionality. We can also send data to one, multiple, or all computers based on what is called a MAC address. Let's talk in networking terms now. What is a collision domain? A collision domain is a physical segment of a network where there is a possibility of signals colliding with each other. Unless otherwise stated in this presentation, all links work in half-duplex mode, meaning that you cannot send and receive data simultaneously. If both devices attempt sending data at the same time, a collision may occur. For this reason, we say the entire region where there is a possibility of a collision is called a collision domain. Although a collision domain may be larger in size, it will still be considered as one collision domain. So, if only PC A and PC B were to exist on this link, this is one collision domain. If this link allows for sharing, other devices may expand this collision domain and make it larger, but it is still one collision domain. A bus network like this one, for example, is a single collision domain network because all links directly connect to one another. If we use a hub instead, we still have a single collision domain because a hub logically functions like a bus network. In summary, a segment consisting of only cables and/or physical layer devices such as a hub results in just one collision domain. What is a broadcast domain? Firstly, we need to know that hubs always send data in broadcast mode, and switches may send data in broadcast mode only when necessary. With this, a broadcast domain is any region of a network through which message broadcasts can be propagated continuously without interruption. Basically, a broadcast domain ends where a layer 3 device exists, such as a router. Let's get this concept from this animation. Assuming PCA sends a broadcast message on the network, it is received by hub A. Hubs send broadcasts by default, so it floods the message and a copy of this message reaches switch A. Switches will always flood messages that are specifically broadcasts. Switch A floods the message to all of its connected interfaces. Looking at the scope of the message so far, all devices are on the same broadcast domain since they receive a broadcast message sent by PCA. This network consists of one broadcast domain. If we attach another network here using a switch and a couple of computers, we can now see that we have two broadcast domains on this network. Why is this? A router will receive and process a broadcast message, but it will not forward the broadcast message into another network. Sometimes, broadcast domains are referred to as local area network segments. Finally, every interface on a hub belongs to the same collision domain. Every interface on a switch belongs to a different collision domain. And every interface on a router belongs to different collision and broadcast domains. With this basic information, how many collision domains do we have on this network? There are 8 isolated segments on this network. When data is generated, it is necessary to attach processing information in every layer, such as how much data is transmitted and identifiers for the device sending the data and the device meant to receive the data, so it can be sent to the right destination. Today, we'll talk about encapsulation. Hello guys, today we'll discuss the concept of encapsulation. Encapsulation is easy. At least one person encapsulates something every day. In real life, encapsulation is like packaging an item to be delivered to a person or organization. Let's take this example of packaging a smartphone as a gift to be sent. First of all, the smartphone is the original data. First layer of encapsulation. We attach a user manual to the phone, giving instructions on how to use it. Second layer of encapsulation. We put them both in a smartphone pouch, large enough to contain the smartphone and the user manual. In this form, it is called a pouch and not a smartphone since the smartphone is enclosed. Third layer of encapsulation. We put the pouch in a box meant for the smartphone. On the box, useful information about the phone is written. In this form, it is called a smartphone box and not a pouch. Fourth layer of encapsulation. We wrap the box as a gift and attach a slip containing the name, phone number, and home address of our recipient as the receiver of the item. In encapsulation, three things happen. First, multiple layers are added to enclose the original data, which is the phone in this example. Second, a new data is formed each time a layer is added. And finally, each layer contains instructions on how to recover the original data in the receiving station. The step-by-step transformation of the smartphone to the gift box is called encapsulation. Similarly, in computer networking, the appending and prepending of protocol information from the application layer to the physical layer is called encapsulation. If this layer of information is added in front of the data, it's called a header. If it is behind the data, it's called a trailer. The main reason for encapsulation is to make data adapt to different protocols and transmission media. For example, any data to which an IP header is attached is capable of being routed on an IP network. In summary, for Ethernet-based networks, application layer data is encapsulated into a TCP segment or UDP datagram at the transport layer. The segment or datagram is encapsulated into an IP packet at the network layer. The packet is encapsulated into an Ethernet frame at the data link layer. Then the frame is encoded as a signal to be transmitted through the physical media. When this signal reaches the destination device, the reverse process is done in order to retrieve the original data. This process is called de-encapsulation or decapsulation. Check out the questions on the next slide. Watch out for the presentation on the Ethernet Hub, same time next week, to get a better understanding on the working principles of the hub as a physical layer device.
Hello guys, welcome to my presentation on the data link layer, and we'll talk about auto negotiation. Some of the parameters that devices on Ethernet negotiate are speed, duplex mode, and flow control. Only the speed and duplex modes will be discussed in this presentation. Speed refers to the maximum supported number of bits that each device can transmit from its interface every second. This is also the rate of data transfer and reception that the network interface card of the device supports. Duplex mode defines the direction-based communication between devices. The duplex modes a device interface support can either be half duplex or full duplex. In half duplex, the sending and receiving of data cannot take place at the same time, while in full duplex, the sending and receiving of data can take place at the same time. The early standard of Ethernet required that all network interface cards used for implementing Ethernet have a maximum speed of 10 megabits per second with a half duplex mode of communication. Everything was going well and devices could communicate properly, except that they suffered a major problem: collisions. The coaxial cables were the first types of cables used for Ethernet connections, and they consist of only one copper wire for data transmission. This is why only half duplex communication can be implemented with coaxial cabling. As technological advancements were fast rising and network requirements grew, the chips on network interface cards were improved to support fast Ethernet. Transmission speeds of up to 100 megabits per second and a full duplex mode of communication were supported. To implement full duplex communication over the physical wiring, the coaxial cable had to be replaced by the twisted pair cables, which allowed for reception and transmission of data over different wire pairs. However, one major problem devices encountered was incompatibility. If you connect two devices together, such that one device was using the old chips that allows a 10 megabits per second transmission, and the other device was using the new chip that supports a 100 megabits per second speed, the device with the new chip will have no problem receiving data at 10 megabits per second, but the device with the old chip will be overloaded and could lose a great portion of the data that it receives. The auto-negotiation technology was designed to solve this problem. It is only implemented in the new network interface cards. Today, network interface card supports gigabit Ethernet, which allows up to 1000 megabits per second transmission speed and full duplex communication. When devices are connected using a cable, they send electrical pulses to each other, which they use to negotiate for optimal speed, duplex mode, and flow control for communication. The negotiation is based on the following. 1. If PCA supports auto-negotiation and PCB does not support auto-negotiation, both devices use the default 10 megabits per second transmission and half duplex mode of communication. 2. If PCA supports auto-negotiation and PCB supports auto-negotiation, both devices choose the fastest speed and best duplex modes supported by both. 3. If PCA supports auto-negotiation and PCB disables its auto-negotiation function, the working mode for both will be based on the working mode of PCB, provided that PCA has those capabilities. 4. If PCA and PCB disable their auto-negotiation function, the working mode that will be manually configured must be the same for both devices to communicate properly. In the event that the link establishment fails, a mismatch of these parameters could be the reason for the failure. Check out the questions on the next slide. What
For a DHCP server to receive a DHCP client broadcast, both DHCP-enabled interfaces must lie on the same broadcast domain or network segment. How does a DHCP server receive the client messages on a different network segment since broadcasts cannot be forwarded across networks? Sometimes, you do not always have to run the race all by yourself. You can relay the packets of the server if there's a relay agent on the broadcast domain of the client. Today, we'll talk about the DHCP relay. Hello guys, we'll talk about the DHCP relay. Why do we need a DHCP relay? Is it to forward DHCP packets from a client to a server in another network segment? While that may sound true, let's look at it this way. A newly initialized DHCP client first of all broadcasts a DHCP discover packet on the network to discover active DHCP servers on the link. If the DHCP server happens to be on another network segment, this broadcast will never get to the DHCP server because broadcasts cannot be forwarded across networks. A quick fix will be to move the DHCP server to the same network segment as the client. However, when the network expands and more devices are connected, it would be uneconomical to install a DHCP server on every single network segment or broadcast domain. Only one DHCP server needs to be configured, while each gateway is configured as what we call a DHCP relay, in some literature referred to as an IP helper. Moving on, Please take a moment to hit the subscribe button and turn on bell notifications so you'll be the first to know when we release a new video like this one. For this DHCP relay setup to function properly, first of all, ensure that there is a reachable route to the DHCP server from the DHCP relay. That is, the DHCP relay knows exactly how to find the DHCP server. And also ensure that the interface on which the DHCP relay functionality is enabled is reachable to the DHCP client broadcasts. When the DHCP function is enabled on the network, UDP port number 67 on the DHCP relays and the DHCP server will be open. And the DHCP clients use the UDP port number 68 for communication. When a DHCP client sends a broadcast packet, it is received on the configured relay interface, and then the relay generates another packet to be sent to the DHCP server. The server then sends the response packet to the relay, which in turn forwards to the client. Finally, all communications between the relay and the server is unicast, and the communication between the clients and the relay is the same as if the client and server are on the same network segment. This means a broadcast discover packet from the client to relay, followed by a unicast offer packet from the relay to the client, and then a broadcast request packet from the client to the relay, and finally, a DHCP acknowledgement message from the relay to the client. This is the end of today's presentation. Please don't forget to hit the subscribe button and turn on that bell for active notifications. Thank you for watching.
Hello guys, welcome to my presentation on MAC addresses. This piece of hardware is called a network adapter or network interface card because on it lies the interface to which you connect network cables. When these adapters are manufactured, a 48-bit value called a MAC address is embedded or burned into them before the hardware is mounted on the circuit board of the device. Any interface connected to any link is recognized by the physical address on that link. On Ethernet links, devices identify each other by using MAC addresses or physical addresses. On a bus network, a frame sent by one computer is received by every other computer on the shared link. After the frame is received, the destination MAC address is verified. All devices discard the frame except the device with the destination MAC address. Every MAC address is 48 bits long and consists of two parts. The first part is used to identify the organization that manufactured this hardware. This value is called the organizationally unique identifier. The second part, which identifies the specific hardware itself, is called the vendor code, vendor assigned value, or serial number. With this structure, it's impossible for two different manufacturers to have devices with the same MAC address. A MAC address used on an interface card is only meant for the device on which the hardware is mounted. However, some special MAC addresses can be generated for special uses. For example, the sending of data to multiple end stations at one time or to all end stations on the link. But how? It's easy for you to read this as $5,000 or this as physical logic. But computers don't understand things this way. They have to break data into its smallest form, called bits. This means the recognized data consisting of only ones and zeros. Each digit in the MAC address is 4 bits. This makes up 48 bits in total. 2 digits here is called a byte. Alternatively, we can say that a MAC address consists of 6 bytes. If we break down the first byte, we'll have 8 bits. Of all these bits, only the last bit here affects how data is forwarded. If the bit at position 8 is a 0, data sent to this destination MAC address will be received and processed by only one device. These types of MAC addresses are called unicast MAC addresses and are used on network adapters. But if the bit is a 1, data sent to this destination MAC address is received and processed by multiple devices. Hence, they are called multicast MAC addresses. To send a frame to all devices on a link, we use the broadcast MAC address of all Fs, which in binary is all 1s. Check out the questions on the next slide. Watch out for the
For how long can a DHCP client use an IP address? A year? Well, whatever that value might be is finally determined in the DHCP acknowledgement message during the exchange process. When a DHCP client successfully obtains IP configuration parameters, it sets various timers to monitor the lease. That is, the period over which these parameters can be used by the client. We'll look at this in today's presentation. Hello guys, we'll talk about DHCP timers. A DHCP client that has obtained IP configuration parameters from a DHCP server with no IP conflict will initialize its TCP IP protocol stack with the new configuration and enter a binding state with the server. It will also set 3 timers to monitor the process of lease renewal, lease rebinding, and lease expiration. These values may be requested by the client during the exchange process or specified in the server configuration. We'll describe the entire process using a default scenario. The default lease time for IP configurations obtained from a DHCP server is 24 hours. This corresponds to the value of the lease expiration timer, which controls lease expiration. Other timers are lease renewal timer and lease rebinding timer. The DHCP lease renewal timer controls lease renewal. The default value is 50% of the lease, that is, half of the lease expiration time. After this period, a DHCP client will enter a renewing state where it will contact the server that allocated its configuration information by sending a DHCP request message in unicast mode to the server. It does this to request for the extension of its lease. It will remain in this state until it receives a DHCP acknowledgement message from the server, after which it enters the binding state and resets its timers. However, if this client receives a DHCP negative acknowledgement message, it enters the initializing state and restarts the DHCP cycle. Moving on, please take a moment to hit the subscribe button and turn on bell notifications so you'll be the first to know when we release a new video like this one. The final timer is the DHCP lease rebinding timer, which controls lease rebinding. The default value is 87.5% of the lease, that is, after the first half of the last quarter of the lease expiration time. This timer expires when a DHCP client does not receive any response from a DHCP server after sending multiple DHCP request messages for its lease extension. This will cause the DHCP client to move from a renewing state to a rebinding state. In this state, it will no longer send unicast messages requesting for its lease extension. Instead, it will broadcast the DHCP request message on the local network segment requesting for lease extension. It will remain in this state until it receives a DHCP acknowledgement message where it will reset its timers and enter the binding state with the DHCP server that acknowledged this request for lease extension. However, if the DHCP client receives a DHCP negative acknowledgement message instead, it must stop using this address and return to the initializing state. Here, it will restart the DHCP cycle. In the event, though, that the client still does not receive a response after many attempts and the lease expiration timer expires, the client must stop using this IP configuration and return to the initializing state, thus restarting the DHCP cycle. We'll discuss DHCP other messages in the next video. Until then, please subscribe and turn on bell notifications. See you in the next one, and thanks for watching.
Colliding with people or objects on your way can be really annoying. Ouch. That one is going to leave a mark. Well, sorry won't fix that. On computer networks, signals can collide on a shared network segment. This causes the original message to be destroyed and makes the link unavailable for a certain period of time. Now, let's find out what is going to happen when collisions occur on a network and how Ethernet solves this problem without having to say sorry. Hello guys, welcome to my presentation on CSMA/CD on Ethernet, and we'll discuss how collisions are prevented and managed on Ethernet-based networks. Collisions can occur on a computer network when two or more devices attempt to send data at the same time through a single wire strand. An example is the bus network, where communication cannot take place in both directions simultaneously. This mode of communication is called half-duplex. In order to prevent collisions on Ethernet-based networks, a mechanism known as carrier sense, multi-access, and collision detection was developed, which applies to half-duplex communications. This is how it works. If PC A attempts to send data to PC B, it uses carrier sense to listen for any ongoing transmission. Since all devices on a shared network segment always receive the sent data, it is easy to detect an ongoing transmission. While listening for traffic on the link, if any other PC is sending data at the moment, PC A has to wait for the transmission to end before it attempts to send data again. In a scenario where PC A listens for traffic on the link and discovers that the link is available, PC A places its data on the link until the transfer is complete. Multi-access. It means data sent by one device is received by multiple devices, which is true for a bus network connection. This means there is a possibility that two PCs may coincidentally listen for ongoing transmission on the link. If they discover that the link is available for use and they send data at the same time, a collision will occur. Now, this is how Ethernet handles collisions. A collision causes two different signals to get mixed up, and this forms a signal having twice the power or amplitude of the original signal. Think of this as the resultant noise effect produced when two people are talking at the same time in a room. The sound gets louder, but nobody gets to be heard clearly. If this happens on a computer network, the devices sending data use collision detection to detect this rise in signal amplitude and immediately stop data transmission, as signals are now unstable and corrupted and would no longer make sense to the receiver. Next, the sending devices send a jamming signal on the link. It basically tells other devices to back off from sending data on the link as a collision has occurred. When devices are notified of this collision, each device runs a back-off algorithm where a countdown time is generated randomly. It is done to allow the existing collision to subside because devices won't transmit data during this time. After these random times are generated, the probability of a collision occurring will be minimal because devices will take turns in sending data based on the device that generates the least time.
Communication between two or more devices on a computer network is defined by various network models, with the TCP/IP model as the most widely adopted for Internet communications. Models are made up of multiple layers, and these layers are made up of protocols or standards which are added in those layers based on the similar levels of functions they perform. Today, we'll focus on the data link layer of the peer TCP/IP model, and in this layer, we will define the Ethernet technology and describe how it is used in creating a link to allow for communication between two or more devices on a computer network. Hello guys, welcome to my presentation on the data link layer, and we'll talk about the Ethernet technology. Ethernet in simple terms mean a link layer technology used for interconnecting devices on a wired local area network. Who defined the Ethernet technology? Being a technology that is not owned by any specific device manufacturer, Ethernet is defined by a standards organization known as the Institute of Electrical and Electronics Engineers, and it was defined under the 802.3 specifications for local area networks. In brief, Ethernet was defined in the IEEE 802.3 specifications. When we talked about the OSI model, we explained that any physical wire is a dead wire until it has a link layer protocol running over it. In order to establish an Ethernet link over thin wire coaxial cable, we need to run the 10^2 Ethernet standard, which in fact allows the cable to transmit up to 10 megabits of data every second for up to a distance approaching 200 meters. The actual distance in practice is 185 meters. Ethernet link over thick coaxial cable can be created by running the 10-base-5 Ethernet standard over the wire. For twisted pair cables such as the category 3, 4, and 5, we need to run the 10-base-T Ethernet standard. Category 5 also supports the running of 100-base-TX Ethernet standard, and the list goes on. Ethernet also includes standards to support optical fiber transmissions as well. Now, how does Ethernet work? Devices supporting Ethernet should have an Ethernet card present on their circuit board. The Ethernet card is a piece of hardware on a device which is responsible for providing Ethernet-related functionalities and data processing. Without it, a computer may not be able to connect to any network. In practice, Ethernet operates at two layers of the OSI reference model. Layer 1. In this layer, it does the encoding of signals transmitted through the physical wiring, and also creates the bit streams that represent the transmitted data. At Layer 2, it is responsible for granting the data access to the transmission media through the Media Access Control sublayer. In simple terms, the Media Access Control sublayer is responsible for placing the data on a link that has been established. How does Ethernet encapsulate data for transmission? In encapsulation, we explained that during processing, a layer may add a header or a trailer to the existing data. The headers or trailers contain information that either define where the data is sent to or how to remove this header and further process the data when it finally reaches the destination device. Every packet entering the data link layer from the upper layers are of different types and hence assigned a type value. These type values are defined by Ethernet and are unique for every packet. Ethernet uses the type value for two things. 1. To identify the packet it is encapsulating, and 2. To determine which of its headers will be used for encapsulating the data. If the type value is 1500 or less, Ethernet will use the IEEE 802.3 header to encapsulate the packet. But if the type value is 1536 or more, Ethernet will encapsulate this packet using an Ethernet 2 frame header. Type values are mostly expressed in hexadecimal form, which can be easily obtained by using a hexadecimal calculator. A hexadecimal number begins with an 0x and then followed by the hexadecimal value. Therefore, frames using the IEEE 802.3 header have a type value equal to 0x05DC or less, and frames using the Ethernet 2 header have a type value equal to 0x0600 or more if these values are converted to hexadecimal. Let's take a simple link layer communication between two end stations. PC A attempts to send a file to PC B using IP at the network layer. First of all, Ethernet assigns IP packets a type value of 0x0800 in hexadecimal form. While the receiver decapsulates this frame, it recognizes the data as an IP packet. Since Ethernet is a technology that allows for multiple devices to share a single link, devices identify each other on the link by using MAC addresses. PC A then adds its MAC address in the source MAC address field. Next, it adds the MAC address of PC B in the destination MAC address field. All of this information forms the Ethernet 2 frame header. Finally, we'll talk about the Ethernet trailer. It contains error checking code called CRC, cyclic redundancy checksum, to determine if this frame has been tampered with during transmission. The field that holds the CRC is a frame check sequence field. It is a value calculated based on the structure of the entire frame, which could be done using a number of methods. The frame is then transmitted using a preamble, which is meant to notify the receiver of an incoming frame. Once the frame is received, the destination MAC address is verified to ensure that the data is meant for this particular computer. Then,
PCB calculates another CRC based on the received frame. If this new CRC is the same as the CRC received from PCA, then it means the frame is intact and not modified. The header and trailer are discarded and the IP packet is sent to the network layer for further processing. However, in the event that both CRC values are different, the entire frame is discarded and not processed further. Check out the questions on the next slide. Watch out for
The process of obtaining IP addresses from a DHCP server isn't exactly like a two-way message exchange process. Instead, it is similar to the process of purchasing a backpack from an online store. You first of all discover available online stores for backpacks through a wide search. Next, each store displays offers for you to make choices. These offers could come in the form of discounts or bonuses. After selecting an offer, you request for the item by making payment. And finally, the acknowledgement comes when the actual item is shipped to your location. This process is similar to the exchange of DHCP messages on a computer network. Today, we'll talk about DHCP operations. Hello guys, we'll talk about the operations of DHCP. DHCP is an application layer protocol primarily designed to provide dynamic IP address allocation services on a network. Services running on servers are reachable through IP addresses and port addresses or port numbers. At layer 3, IP addresses are used for communication, and at layer 4, port numbers are used. These port numbers could be TCP or UDP. Think of TCP as a way of saying that before you send data, make sure to have an active connection to your destination. This gives you control over the data transfer, but for UDP, you don't need to know if the destination is reachable or not. Just go ahead to send the data. DHCP runs on UDP port number 67 on servers, and uses this port for sending and receiving DHCP messages. The clients that request these services from a DHCP server use the UDP port number 68 for communication. Different ports are used to ensure that the DHCP broadcast messages meant for servers are not processed by clients. When DHCP is enabled on a client computer for the first time, it enters a DHCP initializing state and begins to broadcast a DHCP discover message. This is done to find active DHCP servers on the link. As a broadcast message, it is sent to the destination IP address 255.255.255.255 for local broadcast, and the all-Fs destination MAC address. As this client does not yet have an IP address, it uses the source IP address 0.0.0.0, and the source MAC address is the MAC address of the interface sending the DHCP discover message. Moving on, please take a moment to hit the subscribe button and turn on bell notifications so you'll be the first to know when we release a new video like this one. These broadcast packets will be sent at intervals until a packet hits the interface of a server on which DHCP is configured. Only DHCP servers can respond to this broadcast because it is sent to UDP port 67. A server receiving this broadcast will send a DHCP offer message directly to the client, containing the IP address that the server is offering. This DHCP offer packet is sent to UDP port 68. Think of a DHCP offer message as a slip containing a description of the parameters that a server is willing to assign to the client. A DHCP client, on receiving this message, will enter the selecting state. The reason is, more servers may exist on the link, with each sending its own DHCP offer message, as they may have also received the broadcast. The DHCP client preferentially selects the first DHCP offer message received, enters the requesting state, and generates a DHCP request message. The mechanism for selecting a specific offer may be different based on implementation. The source and destination IP and MAC address information for sending the DHCP request message is the same as in the discovery stage. This message is sent as a broadcast at layer 2. One reason it is broadcast is to ensure that all servers whose offer was rejected by the client are aware, so they withdraw their offers. Finally, the server whose offer was accepted by the client then sends a DHCP acknowledgement message in unicast mode to the client. At this point, the client checks the uniqueness of this address, and if unique, enters a binding state with the server and initializes its TCP/IP protocol stack with the received configurations. In some cases, the server may send a DHCP negative acknowledgement message instead to the client after receiving the DHCP request message. More of these concepts will be discussed in the DHCP Other Messages presentation. We'll discuss DHCP timers in the next video. Until then, please subscribe and turn on bell notifications. See you in the next one, and thanks for watching.